So, some quick basic information. Remember when we talked about last week when we talked about exponential functions, or before that we talked about exponential functions. We said b had to be greater than 0 as far as the growth functions. And then b can't be 1. And then the inverse of that would be the logarithm where b can't be less than 0 and b can't be 1. We looked at that first day we looked at logs, we tried to take the log base -1 or tried to take log base of 1, log base 0. We saw that those didn't work. So just some general rules about logarithmic functions. We're just going to look at basic toolkit functions for exponential functions and logarithmic functions. So if we get some kind of information about them. So if we're talking about f of x equals b to the x, okay, basic logarithmic function. It's a continuous and one-to-one function, which means it has an inverse, which of course is important for what we're doing here. Think about plugging numbers into that. We can plug in any number we want into that. This is 93, Madeline. I can take b to any power, b to negative 5,000 power, b to the 5,000 power, b to the 0 power. That's okay. So we're allowed to plug in any number we want into that function. But what will come out of it? Okay. So b to the 0 is 1. B to the second is whatever b squared is. B to the negative second is some fraction. Right? And so that idea that no matter how negative the number gets, we still get some positive, tiny little fraction. And so the graph never went below 0. Okay. If b is greater than 1, if b is a growth function, then the function always increases, right? And it never decreases. If b is a decay function, so it's somewhere between 0 and 1, then that function never increases, it always decreases. And we talked about that a while ago when we were doing the exponential applications, okay? But their domain and the range are both the same. This doesn't matter if it's growth or decay, the domain is all reals. Doesn't matter if it's growth or decay, the range is still 0 to infinity. All right, so it doesn't matter which one of those. And same thing, it doesn't matter if it's growth or decay, it still has the same horizontal asymptote of 0. All right, so we have that y equals 0, which is that horizontal line that the graph does not go below, right, or touch. And then the key points to an exponential function are when you plug in 0, b to the 0, no matter what b is 1. And then when you plug in 1, no matter what b is, you plug in 1, you get b back. So 1b. Those were the key points to that function. So if it was 2 to the x, then it'd be 1, 2. If it was 1/5 to the x, it'd be 1, 1/5. And those were the key points, the easiest points to plot when you're doing an exponential function. So if we take that information that we just got here and we say, hey, let's graph this real quick. And we have our asymptote, y equals 0. We got these points here, 0, 1. And I'm looking at 3 to the x, so 0, 1, and then 1b would be 1, 3. So we can use those 2 points and then what we generally know about exponential functions to just sketch this out. Okay, we don't need more information. All right, so we have those 2 points. That's really enough, because what we know is as we go to the left, that graph is just going to approach that asymptote and then scoot along the side alongside that asymptote. As we go to the right, it's going to shoot very quickly up. So I don't really need much more information in order to draw this. On the left side, I'm going to scoot along the asymptote, kind of parallel to it, curve towards that first point, and then curve steeply up to the left, to the right. So I can get away with just 2 points there. So how can we use what we know about exponential functions and knowing that these two are inverses to help us fill this out? How can we use what we know about exponential functions and knowing that these two are inverses to help us fill this out? Okay, domain and range are flipped, right, Rhea? So the domain of the exponential is the same as the range of the logarithmic. The range of the exponential is the same as the domain of the logarithmic. So what about this? I'm going to skip down to here. The exponential function has a horizontal asymptote of y equals 0. What about the asymptote of the logarithmic function? These are inverses. What would the asymptote here be? Yeah, right, yeah, good. Inverse of that would be x equals 0. I remember the key step to when we did inverse functions back on page 84, right? Was blah, blah, blah. Then step 3 was that key step where it said flip x and y, right? So if exponential functions have a horizontal asymptote, the inverse would be a vertical asymptote of x equals 0. And then if our key points are 0, 1, and 1b, what would be the key points over here? What are our key points here?
Would it be 1, 0?
1, 0, and what else, Grant?
B0?
Not B0. Why'd you say 1, 0?
Because they had flipped. So would it be B1?
There you go. If it was 1, 0 and then B0, then that would not be, those two different x values would give you the same y value, which means that that function is not 1 to 1 anymore. Pretty bad. So realistically, guys, you guys need to know these. If you're going to graph a logarithmic function, you need to know these 2 points. With exponentials, we can generate the points because you can just throw x values at this and get values out to plot. With logarithmic functions, it's really hard to know what x values you can plug in here and get good points. Okay? I can throw -1 at this, I can throw 0 at this, I can throw 1, 2, 3, I can get different points out of this very easily just by changing the x value. So like changing this x and knowing which x's are easy to use is much trickier with a logarithmic function. Okay? So you really need to know these 2 points as a way of starting your problem. There's really no way to get around that. Okay? I'm going to sketch the graph before we go back up and fill in the holes that I left blank there. So I want to graph log base 3 of x. Okay, I'm going to quickly talk about why these points work. Okay, so why is 1, 0 a good point? So if I say, log base 3 of 1, right, my x value is 1. And my x value is 1, log base 3 of 1. What does log base 3 of 1 mean? What does log base 3 of 1 mean? Victoria, what does log base 3 of 1 mean? what question is being asked right here?
Is it 3 to the what?
I didn't hear the last thing you said. If you said something, I just heard 3 to the what?
Yeah, no. Is it 3 to the what power equals 1?
3 to the what power equals 1, right? And so then 3 to the what power equals 1, right? So that answer there is 3 to the 0 power equals 1, right? So why is 1, 0 a point? Because when I plug in 1, the answer must be 0. 3 to the what is 1, and the answer there is 0. Thank you. And so why is 1, 0 a point? Yeah. And so then the other point was supposed to be log, was b1, right? Why is b1 a point? Well, our b value, our base, is 3. So in order for me to, so that means that this would be 3. So what does log base 3 of 3 mean? Colby, what does log base 3 of 3 mean? Three to the what equals 3, right? So, well, 3 to the first equals 3. So log base 3 of 3 equals 1. So we can see why plugging in 3 gives us 1 as an answer. Okay. But are you guys going to remember, here's how, what numbers are you going to plug in? Okay, that's the hard part. Right? And so that's why if we just memorize these 2 points, we're better off. Okay? 1, 0 and b1 are the 2 easiest points for a logarithmic function. Okay? The other thing we need down there is our asymptote. So that's x equals 0. And then we just use what we know about exponential functions and since it's going to be the opposite for a logarithmic function. So notice how, as we went to the left here, it scooted along that asymptote. Well, as we come to the left here, it's going to scoot along that asymptote. So it's going to curve down along that asymptote. So as I go to draw that, okay, so I can start down there low, right next to the asymptote, curve towards that first point. As we head off to the right, it should be a pretty flat curve, kind of like the square root or kind of like the cube root graph, how it goes pretty flat off to the right. Okay, and then down very steeply to the, down and left, very steep. Okay, but see how we can just use 2 points and then what we know about the general shape of these graphs to have enough, and that asymptote as a guiding post. Okay. So normally with a curve, I'd want you guys to have lots of points, but we can use the asymptote and then just what we know about the general shape to get enough done with 2 points for a sketch. So I wanted to skip over the increasing, decreasing part because it's hard to see sometimes, right? Because we saw it here, it's easy to make sense that if b is greater than 1, that's an increasing graph, and if b is between 1 and 0, it's a decreasing graph, a decay graph. Well, what if our b value is greater than 1 here? Is it still increasing or does it flip around? Right, because all this other stuff was busy flipping. Our b value is greater than 1, and look at our graph. It's going up from left to right. So that part doesn't actually change. The inverse of an increasing graph is still increasing. And it's never decreasing. And the inverse of a decreasing function is still decreasing. And always decreasing. So I wanted you guys to see that here, so we can say, oh yeah, see how it makes sense here. Or we just went ahead and wrote it down. All right, but all the graphing we're going to be doing today is going to be transformational graphing, okay? And realize that you guys get to do multiple choice graphing. So I'll show you guys how to do the graphing, but realize you won't be doing a lot of this work in order to do the graph. And I'll show you guys what you should be focusing on as far as like multiple choice stuff to pick the graphs out easily. Okay, so we will be doing a little bit more work than you guys really need to worry about. But again, I will always highlight back to what you could do to make things easy, multiple choice ways. Okay. The next page goes into domain and range stuff. I'm going to go ahead and just do the domain and range of these, just to kind of two birds, one stone it. So we may not get to these examples, but we've already done it. So, okay, so we'll do the graphing and we'll do the domain and range all at one time. All right. So one thing I want you guys to notice is, it's transformations, right? Stretch, compress, reflections, shifts left and shifts right, and shifts up and shifts down. That stuff hasn't changed the whole time we've been talking about this, okay? Any graphing stuff we talked about, those A and H and K have not, changed what they do, where they are. When we look at an exponential function, it'd be something like A times b to the x minus h plus k. So look where A is. It's in the very front. And you guys really won't see much of A except for reflections. We won't be doing any stretching, compressing with this stuff. You'll see a reflection. That's about it. Okay. But A is what A has always been. Right? It's the stretch and compress, again, which you guys won't need to worry about. And then the reflections. All right, and then we go to H. Okay, look where H is, right? It's up in the exponent, right? H has always been inside the function. Remember, H is your liar. So that's your left and right shifts. That's your liar. So if it says plus 2, that's a left 2. If it says minus 5, that's a right 5. And then we've got K back there at the end. So notice how it's after the function, right? It's not in the exponent, it's after, right? It's at the very end. And that's our good old up and down guy. We trust K. Okay. So that's what it looks like for a exponential function. It's really not that much different for a logarithmic. I'm not going to label this one. I'll just show you what it looks like. So again, A would be in the front multiplying. H is going to be inside, right? Inside the parentheses. Remember I talked to you guys about like that first day we did logs, how I like to put parentheses around my logs, the argument. And here's definitely a reason why. We really need to be able to tell the difference between what's inside the function and what's outside the function, right? What's inside and what's outside. So here the 2 is being logged. It's part of the log. The minus 1 is not. Okay. Remember, a log is something we do to a number. It's like square rooting. So here the 2 is being logged. Here the 1 is not. Okay. And then of course K is back there at the end, not inside the function. So as you look at these guys, that's one of the first things I'd have you guys do is identify that base function. So here the base function is f of x equals 3 to the x. Where's that? What's that 2? Okay, well, I see the 2, but that's not part of the base function. Here, the next one, we have f of x equals, and then 2 to the x. All right, what do we see around that 2 to the x? Okay, well, I see a minus sign, a negative sign, and then I've got this plus 1 back here. Okay, so what I don't want you guys to get to worry about is like this, like how this one's 3 to the x and this one's 2 to the x, and think there's like some stretch or compress here. That's nothing. Okay, this is the function 3 to the x. This is just a completely different function. Right? It's still an exponential function, but it's just a different function. Okay, it's 2 to the x. So there's no stretching and compressing like in that regard. We don't need to worry about that. Okay. If this had like a negative 1/2 times 2 to the x, that would be a compression. Again, you guys will not see that. I'm going to look over this one here on number 4. F of x equals log base 3 to the x. Or sorry, log base 3 of x. There's our base function. This guy has, something adding on at the end of it. I look here at this one. F of x equals log base 2 of x. That would be my base function. This guy's got a plus 2 inside the function and a minus 1 after the function. Okay, but again, this switching from a 3 to a 2 is nothing you guys need to worry about. Okay, as far as like a transformation, that's not a transformation. Okay. So what I'm going to show you guys is transformational graphing. So what we're going to use are those key points to kind of set things up. We're going to take the key points in the asymptote. Okay, those are the things you guys need to be able to identify when you're looking at a function. What are the two key points, and then what's the asymptote? Okay. For an exponential function, what were our two key points? What were the two key points for exponential? 0, 1, and 1b? And then what's our asymptote? Y equals 0. Okay, thank you. So that's where we're going to start. Okay, I want you guys to lightly sketch these in. Okay, so we're y equals 0. And then 0, 1. And then 1b, our b value being 3 here. Okay, and then here's our y equals 0. So we lightly sketch those in. What is this doing to our function? Right 2, right, Ruth? So what we're going to do is take those points and we're going to shift them right 2. There's our real point. There's our real point. Okay? We also need to think about, what about this asymptote? What if we shift this line to the right 2? What if we grab that line and shift it to the right 2? Is it going to change? If we grab this line right here and shift it to the right 2, is it going to change? Ray is saying no, right? That line that goes left and right forever, if I shoved it to the right 2, still going to go left forever, still going to go right forever. Yes, it is not going to change. So that is our actual asymptote. So I'm going to make it more. Okay, so that doesn't change. Shifting right 2 does not change a horizontal line. Okay. Since you guys drew these in lightly, I'm going to kind of get rid of them. Okay, if you just want to ignore yours, go for it. So how do I draw this? I only have 2 points, right? What's an exponential function look like? That right side and its growth, right? That right side shoots up fast. The left side goes along that asymptote. So as I draw this, I'm just going to kind of mimic that. I don't have many points, so I need to think about what I know about these shapes. Along that left side, it scoots along that asymptote, curves up through those 2 points, steep on that right side, not straight up, but steep, flat on that left side. So that shifting right did not change our asymptote. It did shift the points, 2 points to the right. What about our domain and our range? Well, our domain is all real numbers. In the same way, as that asymptote, if I go forever to the left and forever to the right, and I move it to the right too, I'm still going forever left and forever right. So that doesn't change. Okay, so that's easy. The range, well, that was supposed to be 0 to infinity, right? 0 to infinity is an up and down thing, right? Did I change anything up and down? No. So nothing changed here either, right? So a shift right or shift left will not change my my horizontal asymptote, because that's a y line. It will not change my range because those are y values. So it should make sense that a shift left and right will not change y values. Okay. So if we had to do the whole graph ourselves, this is what you guys would have to do. Okay? You guys don't have to do that. You're going to have to pick a graph out of a group of 4. So how do you kind of narrow that down, like that whole process of elimination stuff? Okay. Well, it's going to be easiest for you guys to focus on is that most basic of points, which is going to be 0, 1. Okay. So you're going to walk into this problem saying, hey, that's an exponential. I need to use 0, 1 as my like key point. Okay. What's happening to this graph? It's being shifted right to, well, if I'm at 0, 1 and I go right to, where do I end up? I end up at 2, 1. So then I look for a graph that goes through 2, 1. Okay. From what I saw from the homework, there was only ever one graph that did that. The other one was like going through over here, like at, -2. Right, that's pretty easy mistake to make. Shift it left 2 instead of right 2. There was one that was like reflected, okay, and there was another one that didn't make any sense either. It was like going like maybe it was a decay graph or something like that, or maybe it was over here. Okay, like there was never one that like made another one that was anywhere close to being right. And there was one that went through the point and was like the right shape. The other ones were just like junk. Okay, so like a decay graph that goes through that point, you shouldn't get fooled by. Right? That's very obviously a growth function. Okay, so that's all really you guys need to worry about with that stuff. It seemed like the graphing was pretty easy on the homework. There was not a lot of graphing to do anyways, but if you just focus on that one point, shift it accordingly, look for that point on the graph. It seemed always to me pretty obvious which one was the right one. Okay. Oh, let's try it again. So what I want to think about is those key points, right? 0, 1, and 1b. In this case, b is 2, right? The b value is 2. And then again, the asymptote is supposed to be at y equals 0. Okay. So that's the base function. So as you're looking at the transformations, guys, always just go left to right. Okay. So the first thing I see is that reflection. Okay. So I see a reflection across the x-axis, and then I see that shift up 1. So as I go to move these points like we did with on the last one, you want to go in that same order. Always go left to right. It's really an order of operations thing. The multiplication would need to happen before the addition. Okay, but if we just go left to right, it will kind of take care of itself. Okay, so I want to take each of those points and reflect it across the x-axis. So this is 1 unit away here above. So I go 1 unit below. There's a reflection across the x-axis for that one. This one's 2 units away. So now I go 2 units below. So there's the reflection across the x-axis for that point. Next thing I wanted me to do was shift up 1. So now I would go up 1, up 1, and there's my 2 new points. You guys get how I did that? Make sense, Cole? Make sense, Claire? Tiger, you good? Wesley, you good? So, one thing we notice here is that this point is on the asymptote. That's not good. Okay. Remember what the asymptote is a horizontal line. Horizontal lines, we can shift them up, shift them down. Okay. So this is going to cause a change in our asymptote. So instead of y being 0, it's going to bump it up 1. So y equals 1. Here's our actual asymptote. Okay. The other thing you might notice is how these points are below the asymptote, right, which shouldn't be surprising because they got reflected. And so as I draw this on that left side, I'm going to come up along that asymptote, but on the underside of it, I'm going to curve it down and away. Okay, like this. Something like that. Domain cannot change no matter if I reflect it, shift it, all that stuff. The domain will never change for an exponential function. The range we got to watch out for. So visually now we can see that the graph is doing something very different than it was before. Right? It's going down forever. Okay, and it's topping out just short of 1. So why is that happening? Right? So that shift up is changing that value to 1, right? Just like it changed the value to 1 here, rather than 0. Oops. Okay. Well, then what's that reflection doing? Reflection is changing it so it's flipped around. Okay. So we kind of had a double whammy on our range there. So a reflection will take the range and completely reverse it, as far as like, instead of topping out at infinity, it's going to top out at some number and go down forever. And then the shift up told us where our that number was. So as far as what can happen to the range, you're watching out for shifts up and down and reflections. Those are the way you change the range. We saw last time that the shift left and right did not change the range at all, which again should make sense. Left and right shifts are x changes. Up and down shifts are y changes, right? And range are your y values. And a reflection across the x-axis changes the sign of the y value. It doesn't change anything on the x value. So that's why that range flips. So again, what you guys need to focus on as far as multiple choice stuff, you go to that easiest point, 0, 1, and you say, hey, if I reflect that point, where am I at? Reflections cause a change in the y value, the sign of the y value. There's our reflection. All right, the sign of the y value changes. And then it said go up 1. Well, if I go up 1, that's add 1 to the y value, that'd be at 0, 0. So I'd be looking for a point or a graph that runs through 0, 0 and is reflected. It goes, curls down to the right and goes through 0, 0. And again, from what I saw, there weren't any that were anywhere close to each other. And if you find one that's going curling down and going through 0, 0, that was about it. There was never another one. Okay? It's not like a lot of tricky graphs. You got to pay attention to these little minuscule details. Okay, so I just hone in on that one point. How is it going to change according to my transformations? And then should be able to find the graph pretty easy. Things that are a little bit harder is if I just give you guys the function, I say, hey, what's the range of this? That's a much more abstract idea. Okay, so what do I pay attention to if I gave you a function and say, hey, what's the domain of this function? Or hey, what's the range of this function? Without giving you a graph. Well, if it's exponential, the domain will always be all real numbers. If it's exponential, I need to watch out for my range. Because it shifts up and down can mess with it, shifts reflections can mess with it. Okay. Even shifting to something like e, right, as a base, really doesn't matter. Okay. We still have our key points, 1, 0, and then 1, e. Okay. Remember e, 1, 0, 0, 1. Sorry. Remember e is about 2.72. So 1, 2.7. Okay. So here I'm just looking at f of x equals e to the x. There's my basic function. So everything where 1, 0, 1 is. And then 1, 2.7 should be about there. Kayla, what's this doing to the function? Thanks, right, Ruth. Yep. Piper, what's the -2 doing? Piper, what's this doing? Good night, Andrew. So again, what we can do, again, always just go left to right. So I say that right one first. So point, then do the next, do down 2 next. There. Okay, so that's where our point should be. We've got to watch out for these guys here. Instead of being at y equals 0, where it's supposed to be, we're going to be shifting it down to. There's our asymptote. And those downshifts mess with your asymptote, upshifts mess with the asymptote. Okay. We should be able to take that graph and sketch it out now from what we know about exponential functions. Go off to that left side, should be pretty flat along the asymptote, and curve up through those 2 points. Something like that. Domain, easy peasy. Range, I worry about reflections and I worry about up and down shifts. No reflection, so this is gonna bottom out at our new number, which was -2. And go up forever. And I'm trying to think about doing this without having the picture. Okay? So it's supposed to go from 0 to infinity. This is going to shift it down to -2 to infinity. So how do I do that without having the picture? Okay? It's supposed to go from 0 to infinity. It's going to make it to be -2 infinity. Again, kind of using that idea with how do I do a multiple choice? 0, 1, go right 1. So if I add 1 to my x value, because that's a right movement, it's not an up and down movement, I want to change my y value. And I want to go down 2. I'm going to take 2 away from my y value, not my x value. So I'd look for a point or graph that goes through that point. Okay? Find that point. Again, I really only ever saw one graph that did that. You should have an easy enough time picking it out. Okay, so what did that downshift affect? Affected the asymptote directly, and it affected the range directly. Okay. Anything with the exponential functions you guys want to talk about? Look at some logarithmic ones here. We're just going to be taking all those ideas and flipping them around, right? What are our key points? Going to flip that around. What's our asymptote? We're going to flip that around. What's going to affect things? That's going to get flipped. Okay? Last time we had to worry about those up and down shifts. What's going to mess with us this time? Okay? It's all about inverses. So what are our key points for logarithmic functions? These are the ones you guys need to know. Claire, what are our key points for logarithmic functions? Matt, what are our key points for logarithmic functions? That was my water bottle, swear. Wesley, what are our key points for logarithmic functions? All right, Colby. 1, 0, B1. Where's our asymptote? That's how you spell it. Good, right, Colby? Okay, x equals 0. Okay, so that's where we start all these problems. All right, 1, 0, B1. So our B value in this case is 3. 1, 0, 3, 1. Just kind of sketch that in. Okay. That's what it's supposed to look like. Okay. And what are we doing? Right? That's outside of the function, right? It's not in the parentheses, it's after. Okay? So pay attention to that, right? Inside the function versus outside of the function. It's not being logged. Okay, so that's up 1. Well, if I take that vertical line and I shove it up 1, am I changing it? No. Okay. What we do with vertical lines is we move them left, move them right. Okay? Well, that's what vertical lines do. They move left and right. They're already going up and down forever. So up 1 is not going to change my asymptote. No change there. I could take each one of those points and shove it up 1. So if I think about drawing that, so that flat curve off to the right, and then as we run along the asymptote down, steep along that asymptote. Okay? So flat curve off to the right. Steep along that asymptote on the left side. So here's what our function would look like. Again, what do you guys focus on for multiple choice? Start on that 1, 0. What did we do to 1, 0? We shifted it up 1. Go up 1, that means we're at 1, 1. I look for that 1 point. Probably good to go at that. Okay. Domain of the range. Remember, it flips on this one. The range is the easy one. The range is the one that's set. So if I ever ask you what's the range of a logarithmic function, no matter what, it's always all reals. Okay. The domain is what we got to worry about. There's a limitation of what we can plug in. So because we did not shift it left or right, there's no change in our domain. Okay. Upshift to downshift do not change the domain. You guys will not see any reflections across the y-axis. We don't do that in this class. So you'll never have to worry about the domain flipping on you like that. Okay. Mathematically, it's an option. We just don't do it in this level. And if we reflect it vertically, that doesn't change the x values. So, doesn't matter. Okay. Finish this one up real quick. So my asymptote is supposed to be at 0. It's supposed to be at 1, 0. It's supposed to be at 1, 2, 1. There's our 1, 0, B1. This is going to go left 2 and down 1. So if I take those points, I shift them left 2. So there, go down 1. There, there. You can see all those points, they went across the asymptote because this is going to shift the asymptote. X equals -2. It's no longer at 0, it's now at -2. So there's that left and right shift messing with our asymptote. Graph would curve. Let me erase this junk here that we didn't need anymore. Now we're about out of time here. Curve through those 2 points, flat on the, or curve up on the right, flat along the asymptote on the left. Just looks something like that. Range, easy peasy. Domain, stop and think. We shifted everything to the left 2. Still goes right forever. How it affects the domain there. Okay. I'll give you guys a review tomorrow. I'll have time for homework questions tomorrow. All right. Let me know what you need. See you then.
Thank you.
Thanks for help today, guys.